talking about conservative versus non-conservative forces. So this is a principle on your formula sheet. By the way, if you go to where the constants and the units and everything are on your data sheet, you'll see a bunch of physics principles. A bunch of them we've learned, and these are going to come into play every once in a while. You know, a question will ask you what physics principle is at play here, and you'll have to kind of look at all those principles and say, okay, so this is number 5, which is conservation of energy. But of course, we know energy is conserved, it's just transferred to one thing to another, but it depends on what kind of force is being used to what it's being transferred to, right? There's a nice direct transfer if we have things like conservative forces, okay? What's a conservative force? That's where work doesn't depend on the path taken, right? It's only the initial final positions I care about. So for example, with gravitational potential energy, I can move something up in a weird way and like where it's looping around and everything like that. But I don't care about that. It's just like, okay, how high is it off the ground? That's all I need to know. And that's going to tell me it's gravitational potential energy, right? It's going to be the same thing with elastic and electric energy, which we'll learn a little bit more about. So those are conservative forces where really, I know with a conservative force, I can just like directly transfer gravitational potential energy right into kinetic energy. And it doesn't matter what path I take because I know it's going to go right down once it transfers to kinetic energy. Non-conservative forces is ones where the force kind of dissipates the energy. Okay? So that's when it depends on the path taken. Right? So conservative forces, we don't care about the path. That doesn't make a difference. But non-conservative forces means the path taken does matter. What's a force we know that dissipates something? That if you take a longer path, it'll dissipate even more. Friction, right? If you move something more, friction is going to dissipate that how much it's moving more and more and more and more. Right? Air resistance is another form of friction, so it's also going to work like that. The tension in a cord can be a dissipative force. Okay? So those are non-conservative forces. Also, a push or a pull could be non-conservative force, but that's like an additive. That's not one that naturally happens. That's one that you make happen, right? So it's an additive force, a push or a pull by a person. And if you're the person, what path you take does make a difference, right? So those are my non-conservative forces. So why does that matter? Well, when we're talking about conserving mechanical energy, it matters if we're talking about something with conservative forces or non-conservative forces. Because guess what? Oh, first of all, do you guys remember what mechanical energy is? Mechanical energy is the sum of kinetic and potential energies at any moment. Okay? So again, mechanical energy, kinetic plus all the potential energies at any moment along something's path or movement or not movement, because of course, if something's not moving, it still has potential energy. And so we talk about mechanical energy conservation. Mechanical energy is conserved sometimes. It's definitely not conserved all the time. When is mechanical energy conserved? Only if conservative forces are acting. Okay? And then, therefore, it is constant. So energy before is equal to energy after. But that's only working if we have conservative forces. So as soon as friction is at play, no conservation of mechanical energy. Still a conservation of energy as a whole, but not conservation of mechanical energy. Okay? So we will get into more of that conservation of total energy, not mechanical energy, more in the next video. But this one, I'm just going to talk about mechanical energy conservation, a little bit of review from Science 10, and then just adding a little bit more to it. Okay? So again, say we have our conservative forces, so therefore mechanical energy is conserved, then we know the energy before is equal to the energy after. So initial energy, the sum of all the initial energies should equal to the sum of all the final energies. Okay, that's what it means when energy before is equal to energy after. Take something like halfway through its drop, You need to add its kinetic energy plus its gravitational potential energy. And then once it's dropped down to the ground, it's all gone down to kinetic energy and there's no potential. But I need to add them all together, okay? And remember, we could have kinetic energy, we have gravitational potential, we could have spring potential energy, we could have it all. So in that case, I want all the initial energies, so kinetic, gravitational potential, spring potential, should equal to all the final energies, the final kinetic plus the final gravitational potential plus the final spring potential energy. Okay, so that's what the 1 and 2 means. You could also put I and F there for initial and final. And then, of course, we have equations for all of those. So, of course, kinetic, 1/2 mv squared, gravitational potential, mgh, spring potential, 1/2 kx squared, and then all those initially add them together, and that should equal the sum of all of those finally. Now, do we ever use this whole thing? Because this is gross. Like, look at that. No, of course we don't. What do we usually choose as our initial and final things? Usually your initial is like something like where it's at its highest position or where the spring is fully compressed but it's not moving. And your final bit is like where all the potential has converted to kinetic. So then, so we choose our moments smartly, in a smart way, so we don't have to have all this at the same time, because there's plenty of times throughout something's movement where it only has one type of energy or two type of energies, and I don't have to worry about them all. Furthermore, we only sometimes work with spring potential energy, and then sometimes we work with spring and gravitational potential at the same time. That's if you have a vertical spring, and we will do one example like that. But that is by far from every example we're doing. So if there's no spring, even in the situation you're looking at, then you just completely get rid of that, right? So though this looks gross right now, please don't be intimidated by it, because it's very, very unlikely that your final and your initial moments will have all three types of energy. So, for example, let's start with one that you probably went over in grade 10. You drop something from the top of a cliff. Okay? So what kind of energies do you have at each point? Well, here we'll call this your initial, right? Where you haven't dropped it yet, but it's above ground. Okay? It's getting ready to be dropped. So at this point, we don't have any velocity because you haven't dropped it yet, but it's got that potential energy. But does that mean it has kinetic energy? No. So your kinetic energy is 0 here, okay? But here's where your potential energy is at its maximum because your height is at its maximum, okay? So that means your potential energy is at its maximum. And is there a spring at all here? Is there any spring? No, an object is just being dropped from a cliff. So then we don't even care about spring potential energy. We're not even going to talk about it because what's the point? Okay? So that's really, really important to know. That's why, we're going to choose our initial moments and our final moments really carefully. So then we don't have to worry about the sum of all the energies is equal to the sum of all the energies. Because if you pick a point where, okay, the sum of all the energies is kinetic energy is 0 and potential energy is at its maximum, and you're like, okay, well, at this highest point, my entire mechanical energy is just the potential energy. And then sometimes in the middle, sometimes you'll have to deal with things in the middle, right? Every once in a while, I want to know the velocity right here, right? About halfway down. So I'm going to say, well, there, it's likely that kinetic energy is at half or something like that. Or what if I want to know the velocity there when the height was at half of its max, right? So I'd say, okay, well, there's where the height is 1/2. So I know my potential energy is equal to half of the maximum that it was at. Okay? And so then that means half of it, the potential energy, has converted into kinetic energy. So now kinetic energy is at half of its maximum, right? And then I can find the velocity from there. because I know kinetic energy is equal to 1/2 mv squared. Okay, so that's going to be, half the maximum, so it's going to be half and half. Potential energy, half kinetic energy. That doesn't mean that velocity is going to be halfway to its maximum, because kinetic energy is proportional to velocity squared. So just remember, this is accelerating. So that doesn't mean velocity is going to be halfway there. It just means kinetic energy is going to be halfway to its maximum. But that's when that's going to happen. So sometimes it does say, what's the velocity halfway down? And then you will have to find that out, because we can find what half of the potential energy is, right? So the maximum potential energy. But then a lot of the time we'll use this as our final point, where the height is 0. So guess what? If the height's 0, I no longer have any height, right? So if my height is 0, then my potential energy is 0. And therefore, my velocity is at its maximum. So my kinetic energy is at its maximum. Okay? So again, the whole point here is, what do we do when we're looking at initial energy equaling final energy, and we set this scary thing up where we're like, the sum of all the initial energies is equal to the sum of all the final energies. And then we had this crazy scary looking thing over here. We're like, but wait, initially what did it have? Did it have kinetic energy? No. Did it have spring potential? No. Just had gravitational potential energy. Finally, did it have any kinetic energy? Yes. Gravitational potential? No. Spring potential? No. Oh, so that actually then breaks down as something really nice. And then I know initially all I have is mgh, my gravitational potential. I'm going to call that hi. And that should equal to 1/2 m times my final velocity squared. So it comes down to a really, really nice equation when you pick your initial and final times really nicely. Okay? So keep that in mind when we're kind of looking at these things. Okay, so yes, we do have this gross thing where initial is equal to final, the sum of all the initial equal to sum of all the final, but usually we choose our initial and final moments pretty carefully. What would be good initial final moments with a pendulum? Okay, so what if I call this my initial moment? Okay, so what's special about this? This is when my height of the pendulum is at its maximum. Okay, so this is when height is at its maximum, which guess what that means for potential energy? It's also at its maximum. Okay, a lot of people don't know this, but at the very top of a pendulum, guess what it's doing? It's changing direction. What do we know about velocity when it has to change direction? For a split second, it comes to 0. So at this very highest height, your velocity is 0 here. So guess what your kinetic energy is? Also 0. So that's a really nice initial position to choose for a pendulum, right? At its highest height. And then what would be a good final one? A lot of people say it's over here. But wait, doesn't that look exactly the same as the other one, except for it's just like the other way? Yeah, so that's actually not it. It's the lowest point in the pendulum that I want to look at. Okay? And if I choose that to be my final, this is where there's no more height, because your height is really just the distance from its highest height to its lowest point. So at this point, it's its lowest point. It can't go any lower because it's attached to that string. Oh, darn it. I just got rid of everything. Sorry, just give me a sec. I'm going to redo that. Okay, so at this lowest point, now my height is 0. Okay, so therefore my potential energy is 0. But guess what happened to my kinetic energy, my velocity? It's at the lowest. All potential energy has been converted to kinetic energy, so my velocity is at its maximum, which means my kinetic energy is at its maximum. Right? So that's what I mean by when we're like looking at, well, I know the sum of all the initial energies is equal to the sum of all the final energies. If my initial moment is where there's no kinetic energy, there's no spring potential energy anywhere, it's all just, guess what? Gravitational potential energy. Sum of all my final energies. Gravitational potential is 0. Spring potential is 0. So 0 plus the kinetic energy is, guess what? Just the kinetic energy. So that's what I mean when I say let's choose smart places, right? To figure stuff out. And that's a lot of the time what we want. Every once in a while, I'll want like something in between. Okay, and as long as you have one of the extremes where it's at the highest height or the lowest height, usually you can figure out one of those in between. It's not too bad. Okay, so let's do an actual example, not one where I'm just like theoretically talking about stuff, but an actual example. Vertical spring. Oh no, vertical spring means that we have to account for spring potential and gravitational potential. So this one will be a doozy. So obviously, yes, I'm going to go over one of the most difficult kind of examples that you could see here, because then you can do all these easy examples. Everything else will be like, okay, that's no problem. Okay, what do I got here? So I have a vertical spring, ignore its mass. We have K, the spring constant, 900 newtons per meter, is attached to a table and compressed 0.15 meters. Okay, here's something you got to know about springs. Okay, so if this is how much it's compressed, and this is like how it is at its normal equilibrium, that's what we call with a spring, that's a negative height. Okay, so something you got to know about springs is when it's at its equilibrium, its height is technically 0. That's when height is 0. So that's a really important thing to note about springs. So there we go. That's equilibrium, and this is when height is equal to 0. Okay, but now we compressed it all the way down to that. So this is when height is equal to 0.150. But since I compressed it, I'm going to say my height here is equal to negative 0.150 meters. Okay, so that's something that's really, really important to look at. That looks like a F, and I didn't mean for it to. Okay, so height here is equal to negative 0.150 meters. Okay, so something to know about springs. So first we want to know what speed can it give to a 0.3 kilogram ball when it's released. So here's another thing about springs. So if there's a ball here, well, I covered it up. Let's get rid of this. So let's say there is a ball right here, compressed, and there's the ball. When is the ball released? It's also released when it's at, guess what? Equilibrium. So look at that. So that's the point at which it'll be released, when height is 0. That's something that's really, really important here. Okay? So that's another thing to know. That's when a ball will release, or anything that's being compressed by a spring will release from the spring, is the moment that the spring reaches equilibrium. Because that's all a spring wants to do. Honestly, you compress it, it's like, no, I want to go back up to equilibrium. You stretch it, it wants to go back down to equilibrium. That's all a spring ever wants to do. It just wants to go to equilibrium. Okay? Let the poor ball go to equilibrium. So when I say what speed can it give to this ball when released? Okay, so here I'm going to call this point A and this point B. A is going to be my initial and B is going to be my final. Okay? So part A. When I'm looking at here, my initial energies, the sum of initial energy is equal to the sum of final energy. I'm going to write out the whole thing. You never have to do this, by the way. But I'm just going to write it all out. Okay, so what's the sum of all the energies? Well, there could be kinetic energy. There could be gravitational energy. There could be spring potential. Okay, X at A squared. So that's my initials. And then I could have all these 3 energies finally as well. Okay? So I'm just writing this all down. You never have to do this, okay? But just so I can kind of show you in this situation. So again, we want to look at our initial. What do we have? What don't we have? This is fully compressed, okay? So again, in this case, initial is part A, is point A. So what do we have? Do we have velocity at that point? No, it's compressed. It's resting there. So therefore, we do not have any kinetic energy. Do we have gravitational potential energy? Here's a crazy thing. Yes, but our height is negative. Isn't that insane? So technically, if the height's not 0, yeah. So that's actually negative gravitational potential energy, if you can believe it. So we actually do have gravitational potential energy at A. How do you know? It has height. It might be a negative height, but it has height. Do we have elastic potential energy at A? Yes, we do, because the spring is compressed. If a spring is compressed or stretched, there's definitely elastic potential. So I have to leave both of those there. And then our final position, okay, we're calling this final for now. Is there kinetic energy? Well, yeah, we're looking for the speed, right? So absolutely it started moving. Does it have gravitational potential energy at B? Is there a height? No, the height is 0. So we don't have that. Do we have spring potential energy at 0? No, the spring is at equilibrium. So we also don't have that, right? So that's the whole point I'm trying to get across, that sure, the sum of all the initial energies equals the sum of all the final energies, but it usually comes down to a much nicer equation. So just don't let it intimidate you too much, because it does get much nicer, right? So then we have mgh at A plus 1/2 kx squared at A is equal to 1/2 mv squared at point B. Okay, and what are we looking for? We're looking for velocity at B. Let's make sure we have everything there. Do we have the mass? Yes, we do. We have 0.3 kilograms. Do we have G? Of course. Do we have height? Yep. Do we have K? Yep. Do we have X? That's the same as the height. So look at that. Isn't that nice? Okay, so we have everything except for the velocity here. So I'm going to rearrange and solve for the velocity. So the velocity at B should be 2 times mgh at A plus 1/2 kx squared at A. So make sure you multiply the 2 by the whole thing, because I'm multiplying 2 by both sides. And then I'm going to divide by m. And then I'm going to take the square root of that. Okay? I'm going to go on to the next page, because I'm going to fully just run out of room here. Okay, so that was velocity at B is equal to 2 times mgh. So again, m 0.30 g. Remember, h was negative. Okay, so please do not forget that negative. Plus, and then we had 1/2 kx squared. So that's 1/2. My k was 900 newtons per meter. K was again negative 0.150 meters, but careful, when you square that negative, guess what it does? It becomes a positive. Okay, so please be careful. And then, so that everything in those square brackets, you're going to multiply by 2, so please don't forget to do that. You can divide that by the mass, 0.300 kilograms, and I'm going to square root it. Okay, isn't it a good thing I moved on to another page? My goodness. So again, what did I just do? I just plugged in the numbers to this guy right here. That's all I just did. If you're like going, where is she getting these numbers in this thing from? Just plug in the numbers for those. You should get velocity at point B to be 8.03 meters per second. Okay, so there you go. That's our velocity at point B. Almost looks like I just wrote a 3 there. So there we go. That's better. So there we go. There's my velocity at point B. Okay. Okay, there's a whole other part B to this question. My goodness. What does part B say? How high above the original position will the ball fly? Okay, so what happened? Well, we gave it at position B some velocity, right? So now it has a velocity here of, what did we get? 8.03. So we know it's going to keep going up because it has velocity, but it's going to slow down as it goes up because, gravity. So this spring is here. It's at its equilibrium. And honestly, like, from B to C, is the spring even working anymore? It's not, because it already gave it velocity. And now at point B, that's like the moment it stops working. So here it looks like at point B, we have all kinetic energy. And at point C, we have all what kind of energy? Gravitational potential energy. So this one actually isn't too bad at all. I know it sounds kind of crazy because you're like, what are we doing? But remember, we just figured out a bunch of stuff about this more difficult position with A and B. From B to C, B is the moment the spring stops working and the spring has no part in making this go up, right? That's just because it had, well, not that it has no part. It gave it its velocity, but now we're considering, okay, we know the velocity it gave it. So I know what it's going up at 8.03 meters per second, but gravity's going to push it down at a rate of negative 9.81 meters per second. So all my kinetic energy is being converted to potential energy. Okay, so when I'm looking at point B or part B here, I'm only caring about that. When I look at sum of all my energies in the initial is equal to the sum of all my energies in the final, here I'm going to say initial is B, because again, why would I go back and choose A? That sounds so gross at this point, because then we just need to like A, if A was my initial, again, I'm having to consider the fact that there's gravitational potential energy and spring potential energy, and then C, there's gravitational potential energy, but it was given kinetic energy in between. So honestly, you can't even go from A to C. You can't choose A to be your initial and C to be your final, because at this point, it's just too much. So my initial here is point B, and my final is point C. Okay? So initially, what do I have there? I just have that kinetic energy. Oh, not kx squared, mv squared. Oopsie. I was saying kinetic, and then I just ended up writing a k. I can't do it. Okay, there we go. Is equal to, again, we just have potential energy at point C there. And that's what I want. I want the height at point C. Okay? So I'm going to take this 1/2 mv squared. Oh, look what cancels out, actually. The masses. So I don't even need mass here. Isn't that fun? So 1/2 v squared is really what I got. And I divide that by g. And I get the height. So that's nice. That's technically the same as saying v squared divided by 2g. So that's kind of what I'm going to change it into. So that was 8.03 meters per second, all squared, divided by 2 times 9.81 meters per second squared. Okay? And there we go. Once we put that in, make sure that you don't use 8.03, but your more accurate answer. You get 3.29. Okay, let's go back, make sure how high above it's, oh, wait. It says how high above its original position. What was its original position? There, where it's 0.150 below equilibrium. So if I actually want the final height, I forgot for a minute how to spell height there. I was like, I before E except for when you spell height. So it's not just a 3.29, and that's how far above equilibrium it went. But remember, we initially compressed it at 0.150 meters, so we have to add that to it just to get its total height above that starting position. So it's actually 3.44. So that's tricky. Make sure once you get the answer, you go back to the question and make sure, did I fully answer this question? So that's a really tough one. Okay, there we go. Example of the toughest one you can get. Since you guys haven't worked with springs much, sometimes I give them like a horizontal spring, and they think they need to take gravity into it, right? And then it's there, and then sometimes it pushes it back there. If it's a horizontal spring, if it's on a surface, we don't need to worry about gravitational potential energy. Then it just has spring potential, okay? So this is definitely the most difficult kind of question you can get, because it has all three energies at work here, okay? And that's why I'm showing it to you. But anytime we know we have just conservative forces at work, then we can just look at initial energy equal to final energy and not worry about friction or anything like that. Just nice conservation of mechanical energy. And that is nice. So get ready for when there's not conservation of mechanical energy, because if you thought this was messy, oh boy, you're about to be in for a treat. So good luck with that.